Hi, y'all. Can't see myself. I'm not sure why, but it said to embed the video, but oh well. So today I'm going to quickly talk about the sun. Obviously, I'm not getting big screen standing up. This is a real short one today. So I just want to talk about the sun. It's out today. I'm doing this a week ahead of time, so hopefully it'll be out the day you see it. The sun. Sun is 93 million miles from us. We call it one astronomical unit. An astronomical unit is a standard unit of measure used to describe the average distance between the sun and the Earth. Everything else in the solar system is measured in astronomical units. Why? Because they're tired of putting on zeros. So 93 million miles equals 1 AU. That simplifies that. It makes it a little easier to understand. You saw this unit when we did the planetary orbits. We're talking about Mercury in the distance and so on. The size is about 109 times the diameter of the Earth. So it is much, much bigger than our Earth. And it's 330,000 times the mass of the Earth. So that becomes really, really important when it talks about the process of energy production from the sun. The bigger the star, the more energy it can produce. So it's about 4.5 billion years old. They believe that it formed approximately the same time as the rest of the solar system, like our Earth and so on. But really, and I want to emphasize this, thus the capitals, because everybody does that these days, it's a very average star. It just happens to be close to us. It's a very average star. It just happens to be close to us. Now, how does the sun give off its energy? Well, it's a process called nuclear fusion. Hydrogen comes together to form helium and a little bit of energy. Now, when you say a little bit of energy, that's per small piece. You know how small helium and hydrogen are, very, 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 very small molecules. For every time this happens, a little bit of energy is given off, but with the mass as being 330,000 times bigger than the Earth, that's a much, much larger nuclear fusion furnace. Now, don't get this confused with like nuclear power on Earth, different process, or nuclear fission. Fission is the breaking apart. Fusion is the coming together. So hydrogen comes together to form helium and energy. Now, that goes in with a little formula you've probably heard of at some point in time, maybe not had it explained, but it's E equals mc squared. Einstein's theory of relativity, mathematical computation, where E stands for energy, M stands for mass, and C is the speed of light squared, or 3.02 times 10 to the 8th meters per second squared. Okay, so when those two things come together, the hydrogen and the hydrogen come together, you would think that 1 plus 1 equals 2, or in this case, 2 plus 2 equals 4. But in fact, the mass of the two pieces of hydrogen that come together to form helium, the two pieces of hydrogen independently weigh more than the final product of helium. And some of that mass is lost. That mass is converted to energy. That mass goes into that M in that calculation, and that's how Einstein calculated the energy that was released by the sun. Now, that's a lot of physics that you don't need to know for earth science, but at least I filled in the blanks so you know what we're dealing with. Now, a star goes through a life cycle, and here's a diagram of it. It starts out as a nebula. A nebula is basically a big cloud of dust and gas. Nebulas in space, if you look at them, are probably the prettiest things you'll see in space. It's Hubble's 30th anniversary this month, and Hubble has a lot of great nebula photographs. There's something called the Cat's Eye Nebula, which looks like a cat's eye. There's something called the Eagle Nebula. They're tremendous. The entire solar system would fit multiple times in one of these nebula. And it's a big cloud of dust and gas. And that cloud of dust and gas begins to have gravity work on it. It pulls it together to form a protostar. Now, depending on how much dust and gas is in the nebula, it sends it on a different path. The protostar is the same for everybody. If it's an average star like our sun, you follow the top path here, it's a main sequence star, and 4 hydrogens, 1 helium. Okay, it's an average yellow star. Okay, it fuses that hydrogen for billions and billions of years. Eventually, that's going to run out. And when that runs out, the star starts fusing heavier elements. Now, when they start fusing heavier elements, it doesn't give off as much heat. The star cools down, the gravity starts changing within the system, and it begins to grow. So it becomes a cooler, larger star. It's referred to as a red giant. You'll see some more of that when we do your lab the next class. And eventually, when that material runs out inside, it sheds off that outer shell. Oh, and by the way, when our star goes red giant, it won't be pretty for us. We'll actually be inside the sun. At least that's what scientists predict. We'll be actually inside the sun. So we'll be crispy critters, and we'll kiss ourselves goodbye. But that is, don't worry, that's in many billions of years. So we won't be around to figure it out, or to see it, I mean. Eventually, it'll blow off the outer shell. We call that going nova. And you'll have a planetary nebula and a white dwarf at the end as a result. Now, if it's a larger star, it becomes a supergiant, or a red supergiant. Now, when it's a red supergiant, that gets a little bit more violent. Some of the largest explosions ever recorded in space are these, what we call supernova. The supernova explodes and blows off the outer layers, and it either goes down to a neutron star, which is a star that's much smaller than the sun, but has multiple times the mass, or if the mass was great enough, it becomes a black hole. Now, a black hole is not a hole. It looks like a black spot in space because it's so strong that light can't even escape. So light gets trapped in the gravity of it. It's very hard to see a black hole. I know they just got the first picture of a black hole last year. The reason it is light can't escape, and the only thing we can see is how the black hole affects stars around it. If you want to imagine kind of how it works, imagine putting a bowling ball on your mattress and trying to roll a tennis ball by it. The ball will get, if it gets too close, it will get pulled in by the curvature of the mattress. Same thing with the gravity. Something traveling too close to a black hole will get caught by the gravity and it will be pulled in. So light can't even escape. So this is the sequence of the life cycle of a star. If it's an average star, it'll take the top path. If it's a large, massive star, it will take the lower path. Got a couple videos today for you. One to give you life cycle of a star, one just for your entertainment purposes, and a few questions. Hope you're having a good day. And tomorrow you've got a lab looking at the relationships of stars. I'll have a video for you if it does not load on your computer to show you what it should have looked like if you could have manipulated the data yourself. Until next time, have a good one.